Thank you, Jonathan. So first of all, this is not causal. So we're not making any causal claims. It's not a study where we automatically go and mine GitHub, though we use GitHub. We don't use stars. So after we heard about Jan and Co.'s research, we went and we redid everything in a different way. So this is mostly the work of Luis Mastrangelo. He's our PhD student. He graduated just now and he got absorbed by the Swiss financial industry. There's still hope for him, so if somebody has a postdoc position, would like somebody like him in his group, contact him. I think we all know that static type systems have benefits. We've just seen this study that proves it. So I think we can argue that they prevent runtime errors. But somehow some developers do not like static type systems too much. They don't like the eggshell they provide, and they try to escape the static type systems in some situations. There are several ways to do that. One is to use some kind of unsafe intrinsics, like foreign function interfaces, unsafe APIs, unsafe blocks in your source code. Or on the other hand, reflection, so either reflective APIs or, and that's what we're focusing on in this paper, casts, type casts. We specifically looked at the use of casting in Java, and we wanted to know why are casts being used? In what way do developers or is code using casts? How frequently do casts exist in source code? What are the kind of patterns of cast usage we find in existing code, and how recurrent are those patterns? The corpus we looked at is indeed GitHub, but given that we didn't like stars, we relied on somebody we trust more, Semel, to extract from GitHub a set of projects, a significant number of projects, that they cared about analyzing with their infrastructure. So what we did is we looked at the projects in LGTM, which were projects Semel cared about, and projects developers pushed into this infrastructure to then do some analysis on. Initially, we got 7,500 projects, Java projects, that contained a total of about 10 million casts. By the time we went and started to manually looking at those casts, some of the source code had moved, disappeared, was unreachable, so we ended up with 9 million casts in 7,300 projects. Some of those projects didn't contain any costs. So 9 million costs were really in 6,000 something projects, and the remaining like 504 projects didn't have any costs. Now, talking about how many costs, how frequently are costs actually showing up in those projects? Overall, we looked at 24 million methods that contained implementation, and out of those, 2.1 million had at least one cost in them. So that's about 8.7% of the methods we studied contained costs. So costs are being used. Now, the question is, how does that differ across projects? We have seen that sometimes projects are tiny and maybe they're not really representative. So we looked at, for each project, what is the fraction of those methods containing costs. We plotted those projects on this distribution here. You see a box and violin plot that summarizes the bulk of the data. The circles are projects, and they're only shown for the outliers to the right. So on the left hand, you have projects with methods with no methods containing any costs. On the right edge, you have projects, and they exist, where all methods contain a cost. But you can see that those are tiny projects. So there are 4 data points there. One of them I know is some kind of server where everything is just in the main method. So there's a single method and by chance a cost. But we didn't just look at those tiny projects. We have projects that go up to 10,000 compilation units, so classes. So the distribution contains all kinds of projects. The bulk of the values of the projects are in the age spread of this box there. So half of the projects sit between 3% and 9% of methods containing costs. Now we wanted to look at those costs and form patterns. And for that, we tried, but it's a bit too much to look at 9 million projects if you want to look at them yourself. And we didn't want to script it and do regexes or something like that. So we said, let's actually look at a small subset of those individually. So we took a sample. We made it 5,000 because that allowed us to say that less than 1% probability we have of missing a pattern that occurs relatively frequently, meaning in 0.1% or more of the costs. So we looked at those 5,000 manually. And as an overview of the 5,000, 100%, roughly 21% were primitive costs and 79% were reference costs. Of the reference costs, a very small fraction were up costs, to be expected, kind of. They seem somewhat redundant, even though in some cases they're actually deliberate there. And 77% of the, like 79% is the total of reference, 77 plus 2. 77 were down costs. Then we also in Java have boxing and unboxing. So there are some costs, very, very few, 11 we found, that are boxing primitive values and 18 that are unboxing primitive values. You have auto-boxing and unboxing, so they wouldn't be necessary, but still in some cases they're there for purpose. Now we looked where those are located. I think Jan mentioned something like that too, tests. So we looked at which ones are actually located in application or library code that those projects really wanted to deliver. That was 69%. And 11% of the costs we looked at in this random sample were located in unit tests. And guess where the other 20-something% were located? No guess? Generated code. So there's a lot of generated code that contains costs, 21%. And we looked at those two. Now, one of the properties of costs is they can fail. So we're breaking out of this type system, we could crash. We could have a class cost exception in Java. So if you put in a cost, you may want to protect somehow against this failure, so you may want to guard it. We looked at the costs and see whether there's a surrounding guard, at least in the same method, or not, or at least we couldn't find it easily. So 29% of those costs had a very close guard that was protecting them against failure. But now let's look at the patterns a bit in more meaningful ways. To do that, first we took a very small sample, a pilot sample that's not included in the 5,000, and we had two authors look at those costs and try to come up with what actually could those patterns be, just to get an idea. And then Louis, the main author, he went and really himself through 5,000 costs. That's a ton of work. I think it took about more than 10 weeks to go through each one of them and look at them. And every week we had meetings together where he came and he said, I saw some that I can't really classify. Could we discuss them? Also, we discussed merging patterns or breaking patterns into different patterns or renaming patterns in those weekly meetings. In the end, after this phase, we had a table of 26 patterns. And now for the paper, we grouped them into 6 categories. First category is what we call guarded costs, and you have 3 patterns there. The blue one is the one I'm going to explain to you afterwards in a little bit more detail. Another group is API, so that's a costs that depend or are kind of guarded by information you have about the API. Then covariance, costs in relationship to covariance or the absence of covariance. Costs with relation to generic types. Costs about type hacking, so where you could say you're putting a cost there, but it's not really to kind of cost the value, not to cost the type. And finally, costs we would say are code smells. They should probably be removed. Okay, so now let's look at those blue ones in more detail. This is probably the most common one, equals. So everybody who's written Java code or seen Java code knows that you may have an equals method. You inherit equals from Java long object. It gets an argument of type object. And so you probably have to somehow downcast if you want to do a value comparison of the different fields. And you may guard that by either instance of or by get class or even other mechanisms. Here is one of the costs that is exactly a cost out of this sample of 5,000, which is classified as equals. This is in the class called difference. And you see there's a downcast in red where you cast obi into difference. And it's protected by an instance of, and then you do the field comparison. Now, this is something that is ugly, kind of, and you would like to avoid it. If you do Java, you use Scala, and you use case classes. You don't need to write those kind of comparisons. If you use Haskell or Rust, you have constructs that allow you to get rid of those things. And even for Java, you could use approaches that generate the boilerplate that we put here. So the cost is, in many cases, not really necessary to put there. Second example is called family, the pattern, and that's in the covariance category. So that pattern is named family because it has to do with family polymorphism, where you have a base family of classes that collaborate to do something. They work together, and then you create derived families, one or more, that inherit from the corresponding base family classes. And because of that and the absence of covariant parameter types, you end up having to cast from base types to derived types in some places. Here is an example. We have step interface, which is in the base family, and we have dynamic SQL row, which is in the derived family, and it inherits or overrides a method called stop running, gets the signature from above, and has to downcast in red one of the parameter types to access extra information that is relevant for the derived family. So this one could encode differently using F-bounded polymorphism or using various approaches that allow you to kind of encode family polymorphism or to deal with the expression problem. Next one has to do with generics, and that's probably the most blatant one. It's using raw types if you have generics. So here is the precondition is there is a generic class C with type parameter T, and so you could use, if you wanted, the raw version of that class, just C, omit the type parameter. And then if you call a method that would return a T, you will get back an object, and you will have to downcast it to actually do something. So this is kind of in use. This is a standard collection class, an iterator, and instead of saying iterator of recipient information, it just says iterator and it's erasing the type, and then you have to downcast. So you could say after 14 years of having generics in Java, maybe this should not be so common, but we did found 176 in the classes that casts that we analyzed who are of this kind. So use raw type is still alive. Next is a strange one for me. I didn't first think about this. This is a type hack. We called it select overload. So if you have overloaded methods, you have multiple methods with the same name, with different parameter types, you may actually cast an actual argument to select which of the methods you would like to call. Here's the example. We have two versions of assert equals, one taking two objects, one taking two longs, and then we have a call site above where you have a value of type long and another value of type object or a subclass of object, capital long. And we put a cast there which is going to unbox that long, and that really is not about the unboxing so much, but it's about I need to disambiguate this call site and need to say I want to have the long version of the method. So I would say this is a kind of cast that's not necessarily an escape hatch from the type system. It's more about an annotation to tell the compiler which method to select. The last one is a code smell. It's called variable supertype. So if you have an expression that consists only of a variable, all you do is access a variable, and you cast that, and the variable is specified or declared as a less specific type than you actually need, then you will have to downcast at some point. So here's an instance of that pattern. You're allocating a kind of lower level class, SAML token renewer. You assign it to a variable of type token renewer, giving up some type information. You call two methods on it that don't need that extra type information, and then you realize you also need to call setMaxExpiry, which is declared in the derived class, so you're downcasting that. So that's clearly not nice. In Java 10 and later, you could even say, I don't actually put the type there, token renewer, you just put var, and it's going to use local type inference to get rid of this problem. So those were a set of patterns. Now one question is, okay, you just went for kind of special cases, and we tried to at least count how many times we found those patterns. Now, a warning after seeing Jan's talk, the distribution I'm showing you is not something I would now base your decisions on directly. So A, we took projects out of LGTM, not a random sample of GitHub projects or something that was taken in a principled way. We did randomly sample the LGTM projects, but the original thing was possibly biased in some direction. And more importantly, the analysis of the patterns was done by one person, by Lewis. He looked at all of the 5,000. We didn't do something that would allow us to do statistics, like inter-rater agreement, have two people independently categorize and then look at do we disagree or agree on each of those things. Okay, so don't base your decisions on that. Forget this is not causal analysis. Okay. Now here we have the 26 patterns in the 6 categories. For each pattern we have a bar. We also said for each pattern, or for each pattern, how many casts we observed in application code versus test code versus generate the code. The blue bars show you the ones I just discussed. You see that the majority was in application code, but for some patterns, they were quite prevalent in other code. For example, factory is quite often used in testing code, or use raw type is quite common in generated code, where you say, I'm generating code that nobody will ever read. Why should I make it nice and precisely typed? I just throw the erased raw types in there and that's enough. Okay, so that was this study. You can see all the patterns described in the paper. We have an artifact where you can download all the classification. The idea is that that might help people who design language features. Maybe it may inspire something, or it may support some of the decisions. It may inspire tool builders, maybe for designing new refactorings to get rid of some of those uglier costs. And developers, maybe it educates them and tells them, look, this is probably not what you should do, or here's how you could fix this, or maybe use a better language. I'd like to thank Max Schäfer and Semmel, who ran our big queries over their database and their projects. Thanks.
All right, we have time for some questions. Thank you. So in one of the first slides, you mentioned also C#. And then you went into Java. So did you actually look into C#?
No.
No. Okay.
No,
Are you planning to?
No.
Okay.
Luis graduated, and that's it.
It has nicer things. So there are several kinds of casts, the good ones and the evil ones, and it would be very interesting to see what's the, I wouldn't say statistics, but what are the observations.
That's a good point. Yeah.
Hey, I was wondering if you also classified any of these casts by whether the cast was for an interface or a class, and was there any difference between the patterns that you observed for interface casts versus class casts?
That's a good question. We didn't actually do that. At least as far as I know, we didn't. Luis had some extra annotations he put in there. Maybe one of them was looking at these distinctions, but I doubt.
Thanks.
So I'm asking you to speculate. You did say at the end that maybe this could be useful for language designers to design language features. So do you have any suggestions about what language features, either existing, might address the kind of casts that you found?
That's a good question. I'm not enough an expert in language design myself to really have a big experience to say which features would be helpful. But I think some of the patterns we had are actually already solved by language features, right? You could use some kind of, like I showed an example, you could use some kind of annotations to generate equals methods, or you could, I guess, use f-bounded polymorphism to encode some of those patterns. So I'm not entirely sure. I can't say, look, here is the language feature or a pattern that has this kind of promising feature to fix it. But I would expect people with a better background in language design than me might, I hope.